So question 4 is another statistics question, but this time focusing more on correlation and line of best fit. We've got some data here of the number of long-footed potoroos that are in a breeding program, and it's in fact a 5-year breeding program. Just note here that the time is in months, so this is equal to the 5 times the 12. Okay, so if we look at here, it says let's do a linear model, so calculate the Pearson's correlation coefficient. So you have to get this data into your calculator. So to do that, you're going to go into your stats, which is number 2. And to save some time for myself, I've actually pre-entered the data into list 1 and list 2. Now, you can generally assume here a lot of the time that the top set of data is always, I know it's labeled it as T, but is going to be your X or your list 1, and then your list 2 is going to be, I guess not your time, but whatever you're trying to measure, in this case, the number of long-footed potoroos. But again, just read the question to make sure that you can make that assumption. So again, just when you enter your data, it's worth double checking, triple checking your numbers to make sure you've got it correct, because this whole question is going to rely on you having these numbers entered correctly in your calculator, and I hate for you to get it wrong and then have to redo the whole question. So just take your time, make sure you're getting these entered correctly. So the Pearson correlation coefficient, which is your R value, you're going to make, once you've entered your data, you're going to make sure that you can scroll around with this white F6 button, get to your calc. You want to go into regression, which is your F3. Your first value there is your linear regression, and you just want to stick to the one that says the AX plus B, so essentially the first option, which is your F1. You get here like the equation of the line, but I guess for now all we care about is that R value. So the R is equal to 0.98. Actually, we might just keep it as 3 sig figs, so 990 in terms of our rounding there. And it says, hence statewise would be considered an appropriate prediction based on the for the linear model for this data. Well, that's actually quite a high value for your R. So you are just going to say it's a very strong positive linear correlation. So just focusing in on these, you want to make sure you've got your positive and then you're very strong here just to get your 1 mark. Coming down, it says tick which model best represents the equation of the least squares regression line. So just coming over here now, you can kind of see the 2.009 that corresponds to this guy here, which is the A on the calculator, and then the B's is 79.45. That's going to be, I guess, this B down here. So it's going to be this guy here. You can see these ones, I've just switched these around, so this can't be right. And then the other one, well, who knows what I've done. It says using the model that you've chosen from part P, can you complete the following sentence? So you want to describe the value for A. Now this value A, you can see how they're also coming from the question, but it's from your calculator as well. For every additional month in the breeding program, the number of potoroos has to be increased because it's positive. And it's going to increase by the value in front of the T. So it's the 2.01. So this is your, I guess sometimes we think of it as a gradient or coefficient of T. So you need both of those to get your 1 mark. Predict the time when the number of potoroos will reach your 300 in the breeding program. A couple of ways you can do this. My preference is to go to the graphics calculator, so go back to your run menu here. Now, before we get to the calculator, what we're essentially solving is we want to make sure that our n is equal to 300. So it's essentially 300 is equal to the 2.01 T plus 79.5. Now we're going to use solven on our calculators to do that. So option calc, and then you've got this F5 here, which is solven. Now it's just setting up an equation and asking the calculator to solve it for you. Again, the calculator doesn't know what a t is really, but you just replace it with an x. And it will rearrange that equation for us to solve for x. It'll always give you this error. We always just press the exit button. And then we want it to have it as a decimal value. So it's essentially telling us that the t is equal to 109.7, or it's equal to 110 full months. Now I'll just pause and then just show us how to do that algebraically over here. So either method is fine. So you can see here just the way we would do it algebraically. So if you're not confident with your calculator, but you prefer the algebra, either way will get you to that 110 months for when the number of potteroos are going to reach 300 in your breeding program. Okay, flip to the next page. So what's happened now is that the 5 years is done, dusted, and the potteroos are released into the natural habitat. And then it shows what happens to them in the next 4.5 years. So this number here is from the last table. And we should come up and we should, see there's the 199. So that number is followed over into the next table, but we're kind of resetting our time, if you like, because we're talking about the next 4.5 years. Okay, so a recording error has occurred in the collection of this data and outlier is present. So you're going to go through these and see which one's the outlier. This one is the first value, and we've seen before that the 199 matches up, so it can't be that one. When we're looking at this one next, we can see just going from here to here, this is the values are decreasing, but if we look at any other consecutive values, we're always increasing. So this one's likely to be the outlier. We'll just do a quick check. Let's make sure the 48 and the 328 is nothing out of the ordinary, but it's not really. We can see that that's kind of snug between those other two values. So the 18,204 is going to be the outlier there. And then it says, okay, go back to the calculators, remove your outlier now. So we're going to remove this guy here. And then it's going to say, then find the least squares regression equation afterwards. So we're going back to menu, back to statistics, which is number 2. I'll just clear my data. And then I'm going to enter mine after I pause the video. Okay, I've just entered my data. Just make sure that you can see here that I've got the 12. And then I jump down to the 24 afterwards. So the 18 has been removed. And on the other side, after 12 months, there were 225 potteroos. And then after 24 months, there was the 261. So the data error or the outlier is being removed. And then again, like I said, every time you enter the data, just do a double check for yourself. Make sure you haven't made any mistakes in your typing or filling out your calculator. So as for the least squares regression equation, once you've entered your data, you're going to go back into calc. You want to go F3 for regression and then press that X value. You're going to go to AX plus B because you can see here that's the form that they want it over there, the question. And then we get our A and B values. Now, we've got to be careful here because it says using correct variables. So we don't actually want to put in the X and the Y, but we want to actually use the values of M and N. So what we calculate, or the Y value here is not, is going to be the N. And it's going to be equal to, actually I might just put it to the side. A is equal to 2.745, 14. And B is equal to 194.6917. Now we don't obviously need all those decimal points when we go and enter it. We might do 2.75, so 3 sig figs or 2 decimal places there. And then 194, I think for this one we'd need at least 1 decimal, 0.7. You could probably keep your 69 for your final result there. So the key word is their correct variables. So you need N and M, and then you want to make sure you brought those values over from your calculator. Now it says using your model. So no matter how many decimal points you've kept up here, either the you want to make sure you use that. And it says predict the time it will take for the number of potoroos to reach 300 after being released into their natural habitat. So again, n is equal to 300. And we are solving, we're going to use our solve n again. 300 is equal to 2.75 m plus 194.7. Menu 1. So remember it was under option, calc, and then F5. And we're just going to go 300, get that equal sign in there. So shift, and then your decimal point, 2.75. It doesn't know what an m is, but it will recognize x, and it's going to solve for that variable. Plus 194.7. You don't need to close your bracket. Press enter. Always comes up this arrow, so just always press exit. And we want the decimal value, so you're going to press S to D or search decimal. And you'll get that m is equal to 38.3, which is approximately equal to 39 months. Okay, again, you could solve that algebraically if you want, but it's only 1 mark, so go straight to the calculator. Now, it's saying comment on the length of time it takes for the number of potoroos to reach 300 if they're left in the breeding program rather than being released into their natural habitat. So we've kind of done the calculations now a couple of times, but let's have a look. So we've got natural, we'll start with this one, habitat. It's going to equal the original 60 months from table 2 plus the 39 months that we've just calculated up here in part F, which is a total of 99 months. So that's to reach the 300. Okay, so we had to add this one here plus the original value, the original time they were in the breeding program. Now for the breeding program, if we just flick back here, this one here, this is the answer that we're here. So C part 2 actually took 110 months to get to that point. And I'll just write that there because we'll probably all forget question C part 2. So therefore, the difference between 110 and 99 is 11 months longer in the breeding program. Oh. And that's it for question 4. So question 5 is a Hungarian algorithm question. So that just means we're trying to optimize or find an optimal solution for an assignment problem. So it could be trying to minimize costs, maximizing profits, or in this case, we're going to be allocating jobs based on hours of training that apprentices have. So if we just have a look at part A, it's saying what does the shaded value of 73 mean up in the table. So we want to know what this guy here means. Now we're just going to have a look at the labels around the table, and we can see here that's got to do with Jacob, and he's diagnosing wiring issues. And the heading up here gives us our last little bit of information, saying it's the hours of training that he's had diagnosing wiring issues. So you can see that that corresponds to that third box. Next one is saying calculate the total number of hours of training that Benji has had as an apprentice. So Benji is along this line here. So we need to add up all those numbers. So it's 57 plus 55 plus 66 plus the 61. And it seems that he's had 239 hours of training over those 4 areas. Okay, part C. The 4 apprentices will be working on a major company project where the 4 tasks have to be completed at the same time. And the project manager wants to allocate the apprentices with the most hours to the jobs. That's not, they're saying it's not possible, and they want to know why. So if we just go back to this table again, the most number of hours in training for the diagnosing the wiring issues is Kelly, but then installing systems it is also Kelly. Repairing systems, also Kelly, and then interpreting drawings again is going to be Kelly. So Kelly can't be doing every single job at once, and so that's why this is not going to be possible. So we're going to write that down below. So we'll just say that Kelly has the highest number of hours training for each task. And so again, she can't be doing everything at once. So that won't work. So then we're going to be trying this next method over here. So the Hungarian algorithm will be applied to maximize the total combined hours this time that the 4 apprentice electricians have been given. Now, it's saying here they've gone from an original way to a reduced way in order to perform the Hungarian algorithm. So we have to do something like this whenever we get a maximizing problem. Okay, if it's a minimizing, we just jump right into the Hungarian algorithm with our row and column reductions. But if it's a maximizing, we've got to adjust the original array first. And when we do that, what we're looking for is the biggest number in the original array, which happens to be 95. And then every value in that original array has to be subtracted from 95. So if I look at the 57 to get to the 38, I start with my 95, which is my biggest number. I take 57 and I'm going to equal the 38. So to write that down, what we're actually doing here, we're going to say that each value in the original has been subtracted from 95, which is the maximum. And by doing that, we've turned this into the minimizing problem, which the Hungarian algorithm can step through really nicely, and which we're about to do in part 2. So saying complete the remaining steps now so that we can actually allocate these apprentices to their jobs. So looking at this array, our first step, we can decide to do either a row or a column reduction. It won't matter, but we will do a row reduction. And when we do a row reduction, what we're looking for is we're looking for the smallest number on each row. And we're going to subtract each element of that row by that number. So we're going to subtract every element by 29, by 16, going to take away 0, which we won't bother with, and then we'll take 13. Oh, I might just line that up a little bit better. So 38 take 29 is going to be 9. 40 take 29 is 11. 29 take 29 will be the 0. 34 take 29 is going to be 5. So I'll just pause there and fill it up. Okay, so that's done. So on my second row there to get that 6, that first element is 6, I've done 22 take 16. Every element is subtracted from 16 on that row. So row reduction is done. Then we've got to do a very similar thing, but for a column reduction. And this time we're going to look for the smallest number in each column and then subtract that from all the elements. So we've got, what do we have? We've got 6, we've got 3, we don't worry about the zeros, and a 4. So we're going to minus 6, minus 3, and minus 4 from each of those corresponding columns. Okay, to get us started, we'll do 9 take 6, which is going to be 3. Now we're going to go down the column. So 6 take 6 is 0. 13 take 6 will be 7. 44 take 6 is 38. I'll just pause again and fill it all up. Okay, so we've now done the row reduction and the column reduction. And then now we're looking to cover up all those zeros. So you want to cover up the most amount of zeros with the least amount of rows. So by putting a line through my third column, I can cover up 4. I can cover up 2 more by doing the second row, and then I've got one more line to go one more 0 to go, sorry, and my bottom row. So I've now got 3 lines, except I know that I've got 4 tasks to allocate. Number of lines has to equal your number of tasks. So in this case, I know I'm not finished the algorithm, and what I have to do now is I've got to adjust some of those elements by firstly finding my smallest number that's uncovered, which is a 1. I'm going to subtract that number 1 from every element that's not covered. I'm going to add the number 1 to where the lines are intersecting each other. So if I'm looking here, I need to add -1 from all these because they are uncovered. And then I'm going to add 1 to these 2 spots in here where the lines are intersecting. So what that looks like underneath, do it carefully, is I'm going to have 2, 7 and 0. Oh, sorry, I also have to subtract 1 from that original smallest value. 1 take 1 is going to be 0. So that's my top row. Now note that I didn't do anything to this 0 here because it was just covered up by a line but not by the 2 lines. My second row, the 0 and the 11 doesn't change, but I have to +1 to that 0 that's covered by the 2 lines, and then I do nothing to the last 0. I'm going to do 6, 3, the 0 doesn't change, and the 1 take 0 is going to be 0. 38 stays as it is. 0 stays as it is. The second 0 though, I'm going to add 1 to it because it's got 2 lines through it, and then the 4 stays. I'll just fix up my lines. And now I've got to allocate, and I can cover, again, I'm looking to cover the most amount of zeros with the least amount of lines. So I can cover 3 zeros straight away with the first line. I can cover 2 with this line down here. And then the other zeros would have need 2 lines for. So now I've got 4 lines and 4 tasks, which is exactly what I want. So the algorithm is ready to stop, and then you can go ahead and allocate from there. When you're allocating, it's probably best to go back and put some, I might just have to come back this direction. So we know we have Benji, we've got Jacob, we've got Kelly, and we've got Sarah here. I'm just going to rewrite because it's a little bit hard. 2, 7, 0, 0, 0, 11, 1, 0. I'm just going to rewrite this just so we can allocate without getting mixed up with the lines. There's a 1. Okay, so now we're going to allocate based on this. Now, when we're looking to allocate, we're looking for each of our tasks. So the first one we're looking at is the wiring. Now, there's only 1 0 here, which is Jacob, so he's going to get allocated to the wiring. We've got installing. Again, there's only 1 0 in that column, so Sarah is going to be allocated to installing. And then with the repairing and the interpreting, it's hard to split, or you can't split Benji and Kelly because they've both got zeros in both of those spots and nothing in any of the others. So looks like we've got 2 solutions to this allocation problem. And in part 3, that's when they actually do want us to write down those allocations. So again, what we decided that Jacob has to do the diagnosing of the wiring issues. We had Sarah has to do the installing, and then the repairing and the interpreting. We're just going to swap Kelly for each. So Kelly in the first one can do the repairing, in the second solution she can do the interpreting, and then we'll alternate that with Benji. So that's our 2 different allocations, or 2 optimal solutions for the allocations. And just to check, they said, well, can you calculate your total experience hours? So just floating up all the way to the original table, and I might just have to change my pens again. We had Jacob was doing the wiring. We had Sarah that was going to be doing the installing, and then we're going to alternate with Benji up here and Kelly down here, and then we can swap those ones, but they should add up to the same. So I've got 73 plus 79 plus 66 plus 90, and I've got 308. So it's going to take 308 hours. And you can check the other solution is going to be the same. Now, a limitation of using the Hungarian algorithm to allocate tasks in this context, I will write them down and then we can talk about them. Okay, so for these limitations, again, just one that we have to list here, but it could be any one of these three that I've listed. So apprentices can't work in pairs or larger groups, so they can't work together to do each task. Personal preferences of tasks is not allowed, so Jacob might really love interpreting the drawings. However, he's been allocated wiring issues, so no personal preferences. And the third one I've just written down is some tasks might take longer or less time to complete than others, so none of that is taken into account. But also it might be something like Sarah, even though she's had more training in installing systems, doesn't mean that that's what she's quicker at. She might have been really struggling with the installing of the systems, but might be really quick at interpreting drawings. So again, none of that is taken into account with this algorithm. And that's it for question 5.